May bagal daw, architects and civil engineers of the future. Welcome to the Eiffel Tower. I mean, welcome to your online class in strength of materials or mechanics of deformable bodies. I am your instructor, Daryl J. Ambalbin. In this video, I will discuss bending stress example 2. The simply supported beam in figure A has the T-shaped cross-section shown. Determine the values and locations of the maximum tensile and compressive bending stresses. So the beam is under a uniform load of 400 pounds per feet from point A to point B over a distance of 10 feet. Also, it is under a concentrated load of 1,000 pounds at point D. First things first, we determine the support reactions at A and B. To solve for RA, which we now assume to be acting upwards, we take summation moment at B equal to 0. So that RA tends to rotate clockwise about point B, hence positive, and its perpendicular distance from point B is 10 feet. And for the uniform load of 400 pounds per feet, to get the resultant, we simply multiply 400 by the distance 10 feet. So this is now the resultant force. If we try to sketch that, it acts at the midpoint of 10 feet. So that from point A and point B, it is located 5 feet. 5 feet from point A and 5 feet from point B. And about point B, this resultant force tends to rotate counterclockwise, hence negative, and its perpendicular distance from point B is 5 feet. And for the concentrated load of 1,000 pounds, it tends to rotate clockwise about point B, hence positive, and its perpendicular distance from point B is 4 feet. Equating everything to 0, we can calculate for RA equal to 1,600 pounds. The positive value indicates that our assumed direction for RA, which is upwards, is indeed correct. And for the reaction at BRB, we also assume it to be acting upwards. We can solve that by having summation moment at point A equal to 0. For RB, it tends to rotate counterclockwise about point A, hence negative, and its perpendicular distance from point A is 10 feet. Again, for the uniform load, we simply multiply 400 by the distance 10 feet to get the resultant force. And it tends to rotate clockwise about point A, hence positive, and its perpendicular distance from point A is 5 feet. And for the concentrated load of 1,000 pounds, it also tends to rotate clockwise about point A, hence positive, and its perpendicular distance from point A is 14 feet. After taking into consideration all the forces and their perpendicular distances, we equate everything to 0. And we can calculate for RB equal to 3,400 pounds. Again, a positive value, which means our assumed direction, which is upwards, for RB is indeed correct. Again, you can countercheck whether RA and RB are correct by having summation Fy equal to 0. If summation of all vertical forces is equal to 0, then RA and RB is indeed or are indeed correct. Now I want you again to solve for summation Fy equal to 0. After solving the support reactions, we're now ready to sketch the shear and moment diagrams. First, we sketch the shear diagram. So at point A, we have an upward support reaction equal to 1,600 pounds. So that means we go up 1,600 pounds. Going from point A towards point B, we have a downward uniform load of 400 pounds per feet over a distance of 10 feet. So that means we add 1,600 and negative 400 times 10. That is equal to negative 2,400. Now, how do we connect these 2 points? We simply connect them with a straight line. And at point B, we have an upward support reaction equal to 3,400 pounds. So that means we add negative 2,400 and positive 3,400, which is equal to positive 1,000. And going from point B towards point D, there is no loading. That means we have a uniform 1,000 from point B to point D. And at point D, we have a downward concentrated load of 1,000 pounds. That means that we add positive 1,000 and negative 1,000. That is equal to 0. Hence, for our shear diagram, we went from 0 back to 0. That is an indication that our shear diagram is correct. Next, we sketch the moment diagram. At point A, we have no couple, so we begin with 0. Next, we notice that in the shear diagram at this point, we have a 0 shear. Now, we have to compute this distance from point A where the shear becomes 0. How can we compute that? Let this distance from point A where the shear is equal to 0 be equal to x. How do we determine x? We determine x by similar triangles. What are the similar triangles? This triangle and this triangle. So by similar triangles, we have 1,600 is to x, this one, equal to 2,400 is to this distance, which is 10 minus x. So this distance is 10 minus x, which is this value. Calculating for the value of x, we find out that x is equal to 4 feet. So from point A, we have 4 feet as the location of 0 shear. Now, how do we determine the value of our moment at this point? We simply get the area of this triangle. So we have 0 plus the area of this triangle, 1/2 base times height. So our base is 4 feet and our height is 1,600. So that is equal to 3,200. So we have 0. From 0, we go positive 3,200. Now, how do we connect 0 and 3,200? So if the graph is linear in shear, it becomes a second degree or parabolic curve in moment diagram. So we know now that 0 and 3,200 will be connected by a parabolic curve. But what is the concavity of the parabolic curve? Is it upwards or downwards? At point A, the parabolic curve should have a positive slope. And at this point, the parabolic curve should have a zero slope. For that to be possible, the parabolic curve should concave downward. Now from this point, we add 3,200 and the area of this triangle, which will have a negative value. So we have 3,200 plus 1/2 base times height. So we have 1/2. Our base is 10 minus x, which is equal to 10 minus 4, which is equal to 6. And our height will be negative 2,400. That is equal to negative 4,000. So from positive 3,200, we go down to negative 4,000. Again, this is linear in shear. It then becomes a parabolic curve in the moment diagram. But does it concave downward or upward? Again, at this point, the slope of the parabolic curve should be 0. And at point B, the slope of the parabolic curve should be negative. For that to be possible, the parabolic curve should concave downwards. And from negative 4,000, we add the area of this rectangle, which is base times height. So we have negative 4,000 plus our base is 4 feet times the height of 1,000. And that is equal to 0. Since this is a horizontal line in shear, it becomes a linear graph, a linear graph in moment diagram. So we connect negative 4,000 and 0 with a straight line. Again, for our moment diagram, we went from 0 back to 0, which is an indication that our moment diagram is correct. In the previous problem, we had a rectangular cross-section. Thus, we had a horizontal axis of symmetry. The neutral axis is easily located. But in this problem, we have a T-shaped cross-section. Thus, we do not have a horizontal axis of symmetry. We need to locate the neutral axis. To locate the neutral axis, we will be applying Variance Theorem. And before we could do that, we are going to subdivide the cross-section into two areas. This will be area 1 and this will be area 2. And we calculate the area of each. For area 1, that is equal to base times height. The base is 0.8 and the height is 8. Area 1 is equal to 6.4 square inches. For area 2, our base is 6 inches and our height is 0.8 inch. Area 2 is equal to 4.8 square inches. Next, we locate the y bar for each area. Y bar will be measured from the bottom. So for y bar 1, or the centroid of area 1, measured from the bottom, that is simply 1/2 of 8 inches, which is equal to 4 inches. And for y bar 2, which is the centroid of area 2 measured from the bottom, we simply add 8 and 1/2 of 0.8. So that is 0.4. So y bar 2 is equal to 8.4 inches. After which we can have Variance Theorem. Given by this formula, y bar times the quantity A1 plus A2, which is the total cross-sectional area, And this y bar now is the neutral axis of the whole cross-section measured from the bottom. It is equal to A1 y bar 1 plus A2 y bar 2. Substituting our values from the above calculations, we can now solve for our y bar. Y bar located from the bottom is equal to 5.886 inches. The neutral axis of the whole cross-section measured from the bottom. After which we can solve for the moment of inertia of the whole cross-section about the neutral axis using the parallel axis theorem, which is given by this formula. I is equal to the summation of I bar I plus AI times the quantity y bar I minus y bar squared. We do note that for a rectangular cross-section, I is equal to, this should be I bar I equal to BH cubed over 12, where B is the base, H is the height. So we calculate and we substitute. For area 1, our base is 0.8. Our height is 8. So this will be the moment of inertia of area 1. Plus, our area 1 is 6.4. And our y bar 1 is 4. Minus our y bar, which we just calculated, 5.886. Then we square this quantity. This is just considering area 1. Next, we consider area 2. For area 2, our base is 6. Our height is 0.8. So this is now the moment of inertia of area 2. Plus area 2 is 4.8. And y bar 2 is 8.4. And our y bar is 5.886. We square this quantity. Now we're ready to solve for the moment of inertia of the whole cross-section about the neutral axis, which is equal to 87.49 inches raised to the 4th power. We now solve for C top. C top is the distance from the neutral axis to the top of the cross section. So to solve for that, we simply subtract 8.8 and y bar, which is equal to 5.886. So C top is equal to 2.914 inches. And for C bottom, that is the distance from the neutral axis to the bottom of the cross section, which is just our y bar. It is equal to 5.886 inches. We go back to the moment diagram and notice that we have a maximum positive moment, 3,200 pound-feet, which is located 4 feet from point A. And we also have a maximum negative moment equal to 4,000 pound-feet located at point B, which is 10 feet from point A. So we will be considering both maximum moments. First, we consider the stresses at x equal to 4 feet, wherein the maximum positive moment occurs. So our m is 3,200 pound-feet. And for the stress at the top of the cross-section, it is given by the formula negative m c top over I, where m is the bending moment, C top, is 2.914, and our I is the moment of inertia of the whole cross-section about the neutral axis, which we just solved recently. Substituting our values, 3,200 pound-feet was converted or is converted to pound-inches. So we simply multiply that to 12 to convert feet into inch. And our C top is 2.914. Our I is 87.49. Our I is in terms of inches raised to the fourth power, and our C top is in terms of inches. So we're consistent with our units. Calculating, our bending moment at the top of the cross-section is negative 1,278.98 psi. So we have a negative stress. We have a compressive stress, which is expected because, again, when we have a positive moment, the beam smiles. At the top is under compression and the bottom is under tension. So it is expected that at the top, we have a compressive stress. Next, we compute for the stress, bending stress at the bottom of the beam, which is given by the formula mc bot over I. We simply substitute our values. The thing that only changes here is our C bottom. Our C bottom is 5.886. Now we're still consistent with our units. We can now solve for the bending stress at the bottom equal to positive 2,583.41 psi. We have a positive stress, a tensile stress, which is again expected because we have a positive moment. And for a positive moment, the bottom of the beam is under tension. So we have a tensile stress. We now consider the stresses at x equal to 10 feet, which is where the maximum negative bending moment occurs. Our m is then equal to negative 4,000 pound-feet. To compute for the bending moment at the top of the cross-section, we have negative mc top all over I, where m is the moment, C top is the distance from the neutral axis to the top of the cross-section, and I is the moment of inertia of the whole cross-sectional area about the neutral axis. Substituting our values, we have negative. Our m is negative 4,000 times 12. Times 12 because we convert feet into inch to be consistent with our units. Our C top is 2.914 inches. Our I is 87.49 inches raised to the fourth power. Therefore, our bending stress at the top of the cross-section is equal to positive 1,598.72 psi. We have a positive or tensile stress, which is again expected because for a negative moment, the beam is not happy. It is sad. It does not smile. So the top of the beam is under tension and the bottom of the beam is under compression. So that the bending stress at the top of the beam is a tensile stress. For the bending stress at the bottom of the beam, we have mc bottom over I. Substituting our values, we get the bending stress at the bottom of the beam equal to negative 3,229.26 psi, which is expected because for a negative moment, the bottom of the beam is under compressive stress. Now, our maximum tensile stress is equal to 2,583.41 psi, which occurs at the bottom of the section at x equal to 4 feet. And our maximum compressive stress is equal to negative 3,229.26 psi, which occurs at the bottom of the section at x equal to 10 feet. So these are our final answers.